I'm sure we'll have a few more people filter in. There's like 100 people in here right now. Barely fit everyone in the room. All right, so we're gonna start talking about solutions a little bit more, which we've already talked about solutions a lot. Notes are over there. We're going to talk in a little bit more detail, but this is just kind of, honestly, what this is going to do is maybe add some explanation to things that I told you last year and didn't really go into a lot of detail about why they are the way that they are, okay? So when we talk about solutions, you guys remember talking about homogeneous mixtures last year, right? Homogeneous, heterogeneous, it was like one of the first things that we did at the beginning of last year. And all that means is it's two things that are so well mixed that you can't really distinguish the parts. Okay? But, and we're going to get to this a little bit more in a minute, but with a homogeneous mixture, how is that different from, say, an element or a compound? What's that? Okay, it's more than one pure substance. How can we tell just by looking at something, maybe not necessarily looking at it, but what can we do to something to figure out if it's actually a solution, homogeneous mixture, or an element or a compound? Okay, we could maybe try filtering it. That might separate it. Now with a solution, a lot of times it will actually go through the filter. But if we do some sort of phase change, like we evaporate the water in the solution or that sort of thing, just a physical change like that can actually separate the two things from one another, right? With an element or a compound, that doesn't work. You have to do a chemical change to separate the parts of a compound from one another. And you have to do a nuclear reaction to separate the parts of an element from one another, okay? Unless you're talking about the electrons, then you don't have to do a nuclear reaction there. Okay, so that's solutions, just kind of a refresher on that. Now there are a bunch of different, and we went over this last year too, there are a bunch of different types of solutions that you can have, so don't think of solution as just a solid dissolved in water. That's the most common type, but there are a bunch of other types here that you can have, and I'm not going to spend a lot of time on that, but there they are. And this is what we just talked about. Solute is uniformly mixed throughout the solvent. Okay, now do we remember what solute and solvent mean? So I'm not sure that I define those in the rest of the notes. Yeah. Okay, good. So think Kool-Aid on this, right? Kool-Aid is sort of like our universal example for a solution. The solute in the Kool-Aid, that's just the Kool-Aid powder, the sugar that you're adding. And then the solvent, the thing that's doing the dissolving, is the water. Okay? Alright, so in solutions, remember, well, I don't know if you remember this or not, but I showed you a video last year where the water kind of came in and grabbed the salt ions, sodium and the chloride ions, and pulled them apart from one another, and then the water surrounded it. So the question here is, as far as energy is concerned, how does that happen? Because a lot of people, when I tell them that, the question that they have is, well, you're telling me this is a really strong bond here, right? The ionic bonds are very strong because they have high melting points. You have to give those a lot of energy to get them to break. So how can water just come in there and start picking them off like that so easily? Okay? And so it's just a question of energy here. The ion dipole forces have to be strong enough, they have to be stronger than the lattice energy in this sodium chloride in order to pull these apart. Okay, and those ion dipole forces actually are pretty strong. So depending on what it is, sometimes those forces are strong enough to pull them apart. And again, we've talked about this before, but here it is, you know, in pictures again. I didn't put this on your notes because I thought it would just look like a jumble of particles without any color. So basically the water molecules are pulling these sodium and chloride ions apart, if this is sodium chloride, and the water molecules are surrounding each of those. Okay, now there's some energy involved with that happening. Oh, this is what I just said. Actually, I thought that was on the slide before. Ion dipole interactions. You guys know what I mean when I say ion dipole forces? Okay, in an ion dipole, like this is the example of the sodium chloride. The sodium and the chlorine, those are the ions, right? Okay, and then the dipole, or the polar molecules, those are the water molecules here, okay? So you've got ion dipole forces, okay? And the water molecule is very polar. And so it's actually strong enough that it can pull these sodiums and these chlorines apart from one another and surround them in the water, okay? And so if you really want to break down like all the energy processes that happen here, there's a certain amount of energy associated with the separation of the solute particles, okay? Now, that delta H, do you think that's going to be positive or negative? In other words, is that an endothermic process to separate the solute molecules, or is that an exothermic process? And asking that another way, do you think it takes energy to separate these things, or do you think it gives off energy when they separate? Okay, so these are all together, right? There are forces of attraction that are causing these solute molecules, this ionic compound, to stay together. Does it make sense that maybe it's going to take some energy to pull those apart from one another? Because they're attracted to one another, right? Okay, so to actually separate them, that's an endothermic process. That takes some energy. Does that make sense? Okay. And then separation of the solvent molecules. Okay, those are the solvent itself, the water. Those molecules are also attracted to one another through hydrogen bonding, right? So to separate those from one another, that probably takes some energy too, right? So these first two processes, the delta H is positive for both of these. Okay? But then the formation of the solute-solvent interactions, that's going to involve a release of energy, okay? Because remember, it's sort of what we've talked about before. To break, now these are intermolecular forces we're talking about, so these aren't necessarily chemical bonds. But to break bonds, it takes energy, right? And when new bonds form, it releases energy. You kind of have to get that stuck in your head, okay? So this process down here, the delta H equals negative, okay? So I put sodium hydroxide into water. I actually had this yesterday. It gets really, 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 really hot, okay? It's a very exothermic process. It releases a lot of energy. So when I add these two together, these top two delta H's here, if I add them, how do you think that compares to this delta H right here? Which one do you think is bigger? If I'm not asking good questions this morning. The two added together? Okay, if these two added together were bigger than this one, then actually we would be giving more energy to the system than it's releasing. Does that make sense? This system is releasing a lot of energy if it's giving off heat, right? So this one actually, this last delta H process right here, for sodium hydroxide, it's giving off a lot more energy, okay? Now, I don't know if you guys remember this from last year, but baking soda and vinegar, when I react those two, it gets, well, okay, that's a bad example because that's a chemical reaction. See, I don't have a really good dissolving process that's in your sphere of experience, but there are some chemicals that I put in my solutions. When they dissolve, the solution gets quite a bit colder. Anything with ammonium in it, a lot of times that will happen. So the reason for that is because these two processes up here are actually bigger than this process, okay, this delta H. So, and this is kind of what I was just saying. This is a little graph for this, okay? It takes energy to do these first two steps, right? The delta H1 and the delta H2 to separate the particles from one another. And then you've got a delta H3 here. That involves a release of energy, okay? If the release in energy, if the delta H3 is bigger than the delta H1 and delta H2, then you have an overall exothermic process. This thing is going to give off heat as it dissolves, okay? Now we're just talking about dissolving, not reacting. And then same thing here. If your delta H1 plus your delta H2 is actually bigger than your delta H3, then that's going to be an overall endothermic process and it's going to absorb energy, okay? Now this next part right here, this is not going to make a ton of sense to you guys because we haven't talked about entropy yet, but I just want you to kind of be aware of this, okay? there are certain processes that I just talked about, like ammonium chloride. You dissolve that in water, it actually gets colder. So the question is, if it has to absorb energy from the surroundings in order to dissolve, why does it even bother? Why does it just not dissolve? Okay, and that's not a question you guys are going to know the answer to yet. Okay, but we know that this happens. It does happen. So there has to be some explanation for it. And the explanation here is entropy. Okay, and that's a term you guys haven't heard yet, but entropy is the disorder or the randomness of a system. Okay, entropy is chaos, essentially. Turns out if chaos increases, that's a favorable change. Okay, the universe likes it when chaos increases. And we'll talk more about that later. Okay, so with that, well, I guess this is an example of one of those when the carbon tetrachloride dissolves in the C6H14. That's an endothermic process. Okay, so it actually gets colder when those two get mixed together. And the reason for that is you have an increase in the amount of disorder in the system. Okay, and so if the disorder increases, sometimes that can offset that temperature change. Not a big deal if you understand that now. Okay. But I just wanted to mention it in case you were wondering, well, why can a system get colder and still dissolve? Student beware. I just thought that was funny. So here's the thing. If a substance disappears when you put it into a solvent, that can mean one of two things, right? It can mean it's dissolving, or it can mean what? It's reacting, right? So just be careful. Just because it dissolves or just because it disappears doesn't necessarily mean it's dissolving. It could also be reacting, okay? So a test for that, if you evaporate the solvent and there's nothing left, then it probably was actually a chemical reaction that occurred there, okay? So that's a good test. If you do a physical change and you can't get, if you don't have the original substance left at the bottom, then that probably was a chemical change, not a physical one. Okay, types of solutions. We've got saturated solutions. And we talked about this last year, at least in my class. I'm not sure if those of you had Ernst got to it. You talked about saturated solutions? Okay. So saturated solutions just means, again, think about Kool-Aid, okay? Kool-Aid works really well for most of these solution things. If you put a lot of Kool-Aid into a pitcher of water, like let's say you just dump 3 bags in there, what's going to happen to some of that Kool-Aid powder? It's going to sink to the bottom, right? Okay, at that point you have a saturated solution. You've got some sitting at the bottom, right? And then you've got as much dissolved in that solution as you possibly can have, okay? So that's saturated, okay? And so typically in a saturated solution, you're going to have a little bit of the solid sitting at the bottom, okay? And it's going to be in dynamic equilibrium with the solute. This is very much like the vapor pressure thing that we talked about yesterday in class. Remember we talked about vapor pressure. You've got a liquid that's evaporating and condensing at the same rate, okay? Same thing is happening here inside this solution. The amount of solid particles that are dissolving is equal to the rate of dissolved particles that are re-solidifying. Okay? So these particles are always moving. You just need to realize they never stop, right? But when you reach an equilibrium, the amount of particles dissolving is equal to the amount of particles re-solidifying. Okay? Or recrystallizing, I guess is probably the official way to say that. Alright? Does that make sense? That's saturated. Unsaturated. Give me an example of unsaturated. Very watered down Kool-Aid, okay? You put, I don't know, 1/4 of a packet into a gallon of water or something, okay? That's unsaturated. You could actually add more of the Kool-Aid and it would still dissolve, okay? The water is not holding the maximum amount of solute particles at that point. And this all has to do with temperature, okay? You have to realize that at any given temperature, that's going to affect the solubility of the solvent. Okay, and then you guys remember supersaturated from last year? Those of you in my class who did that sodium acetate demo, I think actually you did that in Ernst's class too, didn't you? Yeah, where you dropped the crystal in and it sort of spread and solidified the whole, yeah. And then the idea there, supersaturated, is that it's holding actually more than it should, okay? So give me an example of how you could do that. Now, I don't know for sure that this would work with Kool-Aid. Stirring it's not really going to help you dissolve more than you need to. That will help it dissolve faster, right? But it won't help you dissolve more than you want to. Okay, heat up the water, right? Right. So what you'd want to do then, if you were going, and I don't think this actually works with Kool-Aid. It might a little bit. It works with sweet tea. That's a good example. Okay. Yeah, we talked about that last year, right? Sweet tea is very important to the South, and the important thing about sweet tea is that you get as much sugar packed into that tea as you possibly can. All right. So the strategy is you get the tea really hot, right? Because it will dissolve more of the sugar if it's hot. You dump a bunch of sugar into that thing, okay, and then you slowly, carefully let it cool down, and all of that sugar stays dissolved in the tea, okay? So now you have more sugar dissolved in that tea than there really should be there at that temperature, okay? So that's how you make a supersaturated solution. This is sodium acetate, this picture right here. And that's the one that people always use for a demo, because you can dissolve at high temperatures. You can dissolve like 50 grams of this stuff in 5 or 10 milliliters of water. I mean, that's a very tiny amount of water. Think about 5 or 10 milliliters in a graduated cylinder, and then think about dissolving 50 grams in that 5 or 10 milliliters. That's a crazy amount of solid. So then, you know, as soon as you disturb it, sometimes you can even just bump it, and it will all solidify. Okay, what was that? Yeah, we did that. That was the one where, like, I put a little crystal on. Yeah, actually, I bumped it a couple of times on accident. But I also had a little crystal on the watch glass, and then you can actually make a stalactite if you pour it carefully. You guys remember doing that? Did I not do that in fifth hour? Well, maybe it's because I accidentally bumped one in fifth hour. Maybe I didn't get to do that. I don't know. Okay. So then we need to talk about the things that affect solubility, and there's a couple of different aspects to this. One question you need to ask when you're putting something into a solvent is, will it dissolve at all in that solvent? Okay, and the main thing that determines whether or not it will dissolve at all is its polarity. Okay, whether it's polar or nonpolar. This I don't think we really talked about last year, but I mean, all you have to remember is this right here. Like dissolves like, okay? And then you're good. Polar substances dissolve in polar solvents. Nonpolar substances dissolve in nonpolar solvents. So if you can figure out the polarity of the solvent and the solute, then you should have a pretty good idea of whether it will dissolve or not, okay? And you guys know how to figure out polarity because we've done a lot of practice with that this year, right? What's the biggest thing when you're trying to figure out polarity? What's the big word that will help you to... Symmetry, right? Is the molecule symmetrical when you look at the geometry, okay? If it is symmetrical, it's probably nonpolar, okay? If it's not symmetrical, then it's polar. So that's how you'd figure this out. So if you take a look at this, methanol is very soluble in water, okay? Well, what kinds of forces are there on methanol if you're looking at this? What's maybe one of the most important forces on methanol? Intermolecular forces, I should say. Yeah. Okay, hydrogen bonding, right? Do you guys see the O and the H right there? There's a hydrogen bonded to an oxygen, okay? And this is a small molecule, so the hydrogen bonding is probably the most important type of intermolecular force. Well, what's the most important intermolecular force in water? Hydrogen bonding, right? Okay. These two have the same, very similar intermolecular forces, so methanol dissolves pretty well in water. This infinity symbol means it's, you know, it will mix with water. It will dissolve in it, okay? Now, what's happening here? Because these things still have the OH groups on the end of them, but why is this, down here, why do these get less and less soluble in water as you go down? Okay, so when they're bigger, what's the most important intermolecular force now? Remember, for big molecules, London dispersion is a much more important force. You guys remember talking about that? Okay. So this, really, there's a lot more London dispersion attractions going on between these molecules, so it doesn't match as well with the water, so it doesn't dissolve as well. Okay? Does that make sense? So you just got to look at the intermolecular forces that are happening there. Okay? And the more similar the intermolecular attractions, the more likely they dissolve in one another. So if they ask you any sort of question on the AP exam about what dissolves in what, you need to be thinking about intermolecular forces there. Okay. Do you have a practice problem there? Is there not one? Oh, it's after this. Okay, so let's talk about these couple of things. Just a couple examples here of solubility and how that's important. Glucose, very soluble in water because there's hydrogen bonding in glucose. All right. We know that sugar typically dissolves in water, right? Cyclohexane is not soluble in water. Okay. And other examples of things that are not soluble in water, fats tend to be these long chains that have mainly London dispersion forces. So things like butter, fat from an animal, something like that. Those things don't dissolve in water. We know that to be true, right? Oils don't dissolve in water. If you get oil on your hands, water is typically not going to cut it by itself, right? Actually, a really good thing to get the oil off your hands is gasoline, because gasoline is also nonpolar. Now, the problem with that is who wants to put gasoline on their hands, right? But it actually does a really good job of getting that oil off, because the oil will dissolve in the gasoline. It will mix, and the gasoline's a little bit thinner, so that will just, run off your skin or evaporate. Yeah. You don't want to do that in an enclosed space, definitely. And honestly, I wouldn't recommend that. I mean, if you're anywhere near an open flame or something like that, that could be bad. But it is a good way to get oil off your hands. Now, another good way is soap, okay? Because soap has a... yeah, you guys knew that. Soap has a polar end and a non-polar end, okay? And so it actually is very good at, connecting to the water and connecting to the oil, and it sort of helps them to be able to mix with one another. That's kind of what soap does. Okay, so that's an example there of how that solubility thing is useful. Another thing here, have you guys heard of insoluble or water soluble versus fat soluble vitamins? Maybe you've never heard this. There are certain vitamins, you can take as many of them as you want all day and it's never going to hurt you. Okay. There are other types of vitamins, if you take too many, you can actually overdose and it's very bad for you, okay? It has to do with whether they're water soluble or fat soluble, okay? Vitamin A is only soluble in things like fats, okay? So if you take too much vitamin A, let's say that you're, taking vitamin supplements, and people do this now, and you just take a whole bunch of this vitamin A, then why could that be a problem, possibly? It's going to dissolve in our fats. Do we regularly get rid of fats out of our body, like on a very regular basis? Not nearly as much as water, right? I mean, the water is kind of cycling through our body all the time, okay? So you've got these, something like vitamin C. Get as much vitamin C as you want. It's not going to hurt you, right? Because it's soluble in water, and like I said, without being too graphic about it, I mean, we're constantly getting rid of the water in our body, right? So you don't have to worry about that. You're gonna get rid of the vitamin C pretty quickly. But something that's soluble only in your fats, that's going to be stored long term in your body, and that can be a problem if it starts to build up. Okay, so predict whether each of these is more likely to dissolve in carbon tetrachloride or in water. Well, okay, first thing we need to think about here are the intermolecular forces on our solvents. What is the primary intermolecular force on CCl4? Okay, and we might want to just draw the Lewis dot structure just to make sure here, right? But if you do this, what you're going to end up with is a tetrahedral structure. Okay, there's no lone pairs on the central atom. It's very symmetrical. Okay, and I'm skipping the whole, counting and everything, but I kind of know I know the punchline on this one. All right, so that's CCl4. We're talking LDF here, London dispersion forces. Okay, what about water? Hydrogen bonding, right? Most important force there. Okay, so then we just need to see which ones have forces that match up with which thing. Okay, C7H16. We might actually have to draw this out to kind of see 1, 2, 3, 4, 5, 6, 7, 16 hydrogens. I'm guessing that's a completely saturated organic molecule here. Well, here, let's just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay? So if you count, if you put a hydrogen around all the carbons so that all of them have single bonds, that's going to be, you know, all of your carbons and hydrogens. Okay? C7H16. So how symmetrical is that one? No lone pairs on any of the central atoms, right? That's fairly symmetrical there. So that one is also going to be primarily LDF. And also, it's a bigger chain, right? So the bigger they get, the more London dispersion becomes important. So that one, C7H16, is probably going to dissolve better in carbon tetrachloride, CCl4. Okay. Na2SO4. What about that one? Well, what is Na2SO4? It's a salt. Another name for a salt is... I have trouble hearing you guys with these things on. What are you saying? Okay, well, that's the name for it. It's an ionic compound, right? Okay. So, I mean, these are going to be ions, okay? Which one of these are they more likely to dissolve in? Yeah, I mean, this one's a little bit tricky, but this is going to be the ion dipole thing we were talking about before, right? The water molecules, anything ionic is going to dissolve pretty well in water most of the time, okay? So that one's going to dissolve better in water. What about HCl? Okay, HCl is fairly polar, right? I mean, it's not symmetrical at all because you've just got two things, and there's a big difference in electronegativity between the two of them. So this is polar. Water is very polar. Okay, those two are probably going to mix pretty well. And then I2. Okay, I2 is completely symmetrical, right? It's just a diatomic molecule, so that's going to dissolve better in the CCl4. Okay, so this one, CCl4, this one, H2O, this one, H2O, and this one, CCl4. Okay, you guys get how that works? This should make pretty good sense. I think we've beat the intermolecular forces thing to death. All right. So we've been talking about solids in solution. You can also have gases in solution, okay? And solubility of gases is going to tend to increase with increasing mass, okay? And the main reason for that is you get those larger molecules, they're going to actually have stronger attractive forces for one another, okay? So the bigger they get, the higher their solubility, but no gas is very soluble in water. Okay. So you may be thinking, well, London dispersion forces are not like hydrogen bonding in water, so why does that help it dissolve? Okay. What we're talking about here is almost no intermolecular forces versus at least some intermolecular forces, okay? So because these down here, like the krypton, at least there's some intermolecular attractions, then that actually helps them to dissolve a little bit better in water, okay? But, I mean, if we're talking about London dispersion versus hydrogen bonding, obviously something with hydrogen bonding is going to dissolve a lot better than something with London dispersion. So larger gases tend to dissolve better. Liquids and solids, a good way to get sugar to dissolve in your sweet tea is not to put it in a pressurized container. That's not going to do much for you, okay? Here, let's squeeze the sugar into the water, right? That doesn't work. But if you put a lot of pressure on a gas, you can actually get a lot more of it to dissolve in water. Can you guys think of an example of this? We have a very common example of this. Yeah. One of the students in here actually released a lot of pressure from their container, okay, just a little while ago. And the reason that there's so much pressure put on those containers is because it forces the CO2, carbon dioxide gas, to dissolve in the water, okay? And that's why all that pressure's there. And that's why as soon as you take that pressure off, as soon as you unscrew that cap and you hear that release of pressure, all of the carbonation starts to come out of the soda, right? That carbon dioxide didn't want to be dissolved in the water because it's not very soluble in water. So as soon as you release the pressure, it all comes back out. Okay, if you really increase the pressure by shaking it before someone opens it, then all the carbon dioxide comes out really fast, and that's when, you know, that's when it overflows. Okay, you guys ever done the Mentos and Coke thing? Okay, if you put Mentos into Coke, for some reason there's Mythbusters' best idea on this was that it provides these nucleation sites, and all that means is it allows for the gas to escape very, very, very quickly. Okay, so you put a lot of Mentos in there and you have a geyser because the carbon dioxide is trying to get out so fast, it's pushing all that liquid up at a very high speed. Okay, so that's the idea of gases under pressure. There's actually a law for this. Henry liked soda, so he made a law. I don't know if that's true or not, but the solubility of a gas is equal to its K. K is the Henry's gas law constant for that particular gas in that particular solvent. Okay, so there would be a K for CO2 and water. There'd be a specific constant there, and then whatever pressure that gas is at. Okay, and so as you can see, I mean, the main thing you want to see from this formula is as the pressure increases, what happens to the solubility? It also increases, right? These are on opposite sides, so they're directly related. As pressure increases of a gas, the solubility of the gas increases as well. Okay. All right, let's try one quick practice problem here. We're almost done today. Concentration of CO2 in a soft drink that is bottled with a partial pressure of CO2 of 4 atmospheres at 25 degrees. And at this temperature, here's the Henry's law constant. Okay. This is pretty simple. I've actually never seen one quite like this on an AP exam. I don't think they're going to ask you this question. But I mean, it's just kind of interesting to see how this works. Okay, so the solubility of CO2 is going to be equal to K, which is 3.1 times 10 to the negative second. Let's pay attention to our units here. Moles per liter times atmosphere times our pressure is 4.0 atmospheres. So what happened to our units here when we multiply these two together? Yeah, ATMs cancel out, right? That leaves us with moles per liter, which is, what is that? Not density. It's been a little while since we talked about this. Molarity, it's concentration, okay? So this is telling us the concentration of gas we could have in that solution, okay? So 3.1 times 4 is something I should be able to do in my head. That 12.4, all right. What is it? 12.124. Oh, I'm sorry. 3.1 times 10 to the negative second. Okay, I wasn't paying attention to that. Okay, say that again. It's 0.124. Oh yeah, because 12.4 would be if it wasn't times 10 to the second. That makes sense. All right, and again, that's big M or moles per liter, however you want to say that. Okay. And again, I don't think that's one that you really need to know for your AP test. It's not one you need to know for my test. Okay. Last thing here. Temperature affects solubility. Okay, now we already talked about this. If you raise the temperature of something, you can supersaturate it. That works when you have a solid that you're trying to dissolve in a liquid. Okay? For the most part, you increase the temperature, you greatly increase the solubility of something in the liquid. Okay? Now, it doesn't work that well for NaCl. I mean, notice that's pretty straight across the board. It doesn't really matter what temperature the salt is at. It's pretty soluble. It's about the same no matter what, okay? And then there are a couple things, a couple of weird ones like cesium sulfate that actually their solubility decreases a little bit as you increase the temperature, okay? But for the most part, these things are going to increase in solubility as you increase their temperatures. Gases are exactly the opposite, okay? The warmer they get, the less soluble the gas is in the water, okay? That's actually why, now probably the reason that you're putting your soda in the fridge after you open it the first time, it's probably just to keep it cold. But another added benefit is it loses its carbon dioxide, it loses its carbonation slower if it's colder, okay? And that's actually why fish like cold streams better than they like warm ones. I don't know if you guys knew that. There is more oxygen dissolved in cold streams than there is in warm lakes, okay? And so the fish actually prefer I say fish prefer, fish will live wherever they're living, right? But there's more oxygen available for life to be in those cold streams rather than in the warm lakes, as far as life that depends on the oxygen underneath the water, okay? Does that make sense? No? Okay, I'm going to go with yes. All right, so that's it for today. And we'll see you guys in class if you're watching the video.